It is comprised of a Fabry-Perot interferometer and wide-angle camera. I will give an overview, a short overview of the Fabry-Perot interferometer. I hope you see my cursor. So here we see the dome where there is a robotic arm that collects the light from the thermosphere. And here we see the optical part that processes the light coming. And it has to give us some interference pattern. And through Doppler so this robotic arm achieves five measurements in every sequence of measurement, which means it collects the thermospheric wind looking at the vertically, which give us the vertical winds, and 500 kilometers. 500 kilometers, we have the zonal winds, one measurement of the zonal wind in the west and one measurement of the zonal thermospheric wind in the east, and one measurement of the meridional wind in the north, and another measurement of the meridional wind in the west, meaning we have 2 points of measurement of the meridional winds and 2 points of measurement of the zonal winds in 1 sequence of measurement. And it goes on and on through the night, measurement in these sequences. So, so which is important that we have two meridional winds, 2 components of the meridional winds. When we want to over average and have an idea about this, let's see a square of measurement, we average these 2 components and we have the meridional winds. And when we average these 2 components, we have the zonal winds, the general trend of the thermospheric winds. When we want to have a look of what happened in the area, we look closely in each component, all right? We have also a camera. This camera, so both of them, they target, we use the 630 nanometers air glow because it is the brightest, and this is what we have given us more result than the green one. This air glow targets make measurements of the thermospheric winds and temperature at an altitude of about 250 kilometers. And with the camera, we can jointly observe equatorial. Yeah.
How are you doing? Yeah, to enjoy your summer intensive. Yeah.
Let me try to move.
Good to have you back. How was your time?
Okay.
That's fine.
All right, so with the camera, we can observe equatorial plasma bubbles, medium-scale traveling ionospheric disturbances, gravity waves, brightness waves. We have also five GPS stations in Morocco. So it gives us some interesting results just by working with these equipments, and we will see. We had the measurement of the wind and temperature and ionospheric irregularities at 250 kilometers. And we measure, of course, the thermospheric wind and we established the climatology of the thermospheric winds and temperature in quite time, the seasonal effect, the dependence, the effect of the solar cycle, the effect of geomagnetic storm. We studied also gravity wave signatures on using the camera, equatorial plasma, climatology of equatorial plasma bubbles, and the response of the thermosphere to geomagnetic storms. When we use both the FPI, the camera, and the tech, it gives a very interesting result. I will give a summary of some papers that we have published And what interesting results we can get from these equipment. And we use also swarm data, and we compared some empirical models and physics-based models, and we draw some results where some models have to be improved, etc. And which is very important that that it belongs to a network of similar equipments. And it's very interesting because we can complement observation by similar equipment in other locations. In Africa, we have already five Fabry-Perot interferometers. There is already a paper published concerning the presentation of our primary result in these 5 countries, 5 measurements. And hopefully we will publish more, and we will go more into details and comparison and scientific results. And so, and this network can allow for latitudinal and longitudinal study of the thermosphere dynamics and the correlation with the ionosphere. And of course, we can understand time response to geomagnetic storm, etc. So I will just summarize some results. We have observed. As I said earlier, when we average, we have like to say, if we take a square of 500 kilometers in latitude over 500 kilometers in longitude, at this square we have the response, the primary the response, the primary source of the thermospheric dynamics, because it is over averaged here in this figure, the general trend of the thermosphere in the area. We see how far the strength and the dynamics of the winds. For example, I will just give a summary very quickly. For example, they are equatorward, and there is a poleward component in winter time, and from equatorward they shift to poleward. I just have to say that equatorward in zonal winds, meaning negative values are equatorward, positive values are poleward. And it is important to see, sorry, I will come back to this picture. Here is the location of Okeimeden. It is at 30 degrees north, 31 degrees north, and 20 degrees in geomagnetic latitude. So just so when the winds are positive, the meridional winds are positive, they are over the north, and negative, they are over the equator. And when the zonal winds are positive, they are over the west. Sorry, they are eastward, and they are negative. When they are negative, they are westward. So they come to this picture. This wind. This is the meridional winds. They are eastward most of the time, and they have higher magnitude in winter time than in summertime, and they reverse according to season. And we have this very detailed in the paper, and we compare to HWM14 model. Here we have a closer look at the secondary source of the thermospheric dynamics, meaning I took here a daily response in very, very quiet time, and we see the 2 components of the 2 zonal winds, the east and west, and the 2 meridional winds, the north and south, and the vertical wind, which is in black. So it is important to notice that the zonal winds, even though they are 500 kilometers far apart, they stick close together. However, the meridional winds, there is some difference between them. There is sometimes even 50 kilometers per second difference in very, very quiet time. Maybe if we develop some treatment of this component of the wind, we can deduce So the wave that give the daily variation of the thermosphere in this region. For example. Here, for example, it is very important, this figure here in the up right, we witness a breaking of gravity waves that give us some dynamic of the vertical winds. They go up to 50 kilometers per second, and the meridional wind of 200 kilometers per second that we rarely witness in quiet time, and we witness in storm time. So the fact that we measure two components, two zonal wind, two meridionals, are very important for studying the dynamics, have a closer look in the dynamic in the vicinity of the area. So now I will just show very rapidly the seasonal dependence of the zonal and meridional winds. In winter time, the zonal wind are eastward and the highest, and the meridional wind are equatorward and the lowest. All right, and the magnitude diminishes through the season, and this is. They turn westward, from eastward to westward in earlier time during summertime, and the meridional wind they become equatorward and with higher magnitude. Of course, the thermosphere, it's important to see like, for example, in winter time, the thermosphere oscillates between 700 degrees to 900 K, and in summertime, 1100 K to 900, etc. We have just an idea about the thermospheric wind and temperature. The reason why I'm showing these figures, it is the vertical winds. And we do draw a seasonality of the vertical winds in winter. We compare 2 years of measurement, 2014 and 2015, and we see a clear trend with, 3 years, and we see a clear trend and between this seasonality, which means that in modeling the thermosphere, oftentimes we assume that the vertical wind is close to zero, which is not the case. And then we saw the solar cycle dependence, and we started measuring. We had the full year of this is the solar cycle, and with the blue is the availability of the FBI data. Okay. So we have 3 years, 2014, 15, 16, and some of 17, and then 2019, 20, and some of 21. And we have to repair the fabric barrel again and to make it functional, because sometimes it just shut down. All right. So the solar cycle in winter, there is almost no dependence. And of course, the zonal wind are highest in eastward, in the peak of the solar cycle, and they tend to be less important, and even for other seasons. It is for the meridional winds, there is like no difference in winter time, but the equatorward components have a tendency to be to increase in density with the solar cycle in the other seasons. And of course, the thermosphere is the highest in it tends to cool down with the decline in solar cycle. And here we see, on average, the effect of storm time. And we have in the blue, here is the very quiet time, the average of the very quiet time. I give just an example of average of winter 2015, for example. And the blue is the quiet, the other is with Kp greater than 3. All right, and it is averages, so we have ups and downs related to geomagnetic storms. And we see that in winter time, the ups and downs that are not comparable with summertime, for example, and there is a clear solar cycle dependence, and we see just a trend to have an idea of what happened for meridional winds. Though they tend to be close to the quiet time, but with enhanced strength. For the zonal winds, here is the quiet, and the other is the average of winter, for example, 2015. The winds tend to be less eastward and to reverse to westward. Of course, it depends on every single storm, but because this is the average, this is just an average to have an idea. And there is a clear solar cycle dependence that is published in this paper. It is with the detail. Here is a temperature. So in winter, it doesn't heat that much. We have also the average, which is important that in every single storm, there is a wavy pattern with the enhanced temperature and cooling down and then enhanced temperature and so on, though, which means that there is a clear connection, movement from below to up and from up to below. It's very dynamic. Now I am going to present the study. We did a study of on average, we averaged all the storm to have a tendency and to make statistical analysis in another paper. In this paper, just focused on this storm, the 27th February, sorry, 2014, not 2015. It's an error. So in this storm, we had an event particle, and a flare, and a CME. And it was moderate storm with the DST about -100, and the KP about 5. And here we have during the storm, the average between the north and the north meridional wind and the south meridional, to have just a general trend of the meridional wind and the zonal wind. And we see clearly that the winds turn westward, they became less eastward and turn westward. Okay. And by the end of the night, they return back to normal. They turn back to normal, the zonal wind, at least. And here we see clearly, like a traveling atmospheric disturbance trend in the meridional winds, okay? So we have the extent of the winds, the first traveling atmospheric disturbance coming from the north, given the position of the observatory. Observatory can sense in first which is close, meaning the winds coming from the high latitudes, the north, and the 7 traveling atmospheric disturbance, which is trans-equatorial and coming from the south, etc. And we will present later some results. This is the temperature that in this night, the 27th February 2014, this is the temperature. It goes to about 1100 K, and it stays on 1,000 K for a very long time. And as I said, there is still this wavy pattern in the temperature. Here we have the two components of the meridional winds. The blue is the south component, and the red is the north component. And we could identify clearly the two traveling atmospheric disturbances. We could measure their speed, and we find that the speed is about 550 meters per second, etc. I will be in this next slide. I will talk about another phenomena. This is a phenomena we called midnight temperature maximum that is observed in quiet thermosphere. In very quiet thermosphere, we observe this phenomena. It is a reversal of the meridional winds and a subsequent heating of the thermosphere, and just seconds or minutes later, subsequent heating of the thermosphere. Here we have this phenomena observed in the same month, averaged for all copy less than 3. And this phenomena during the geomagnetic storm exceed 100 meters per second. And in quiet time, it is less than 20 meters per second, which is important result to see. And it happened that, oh, sorry, we also compare sorry, sometimes I didn't find my words. The storm component, meaning we, from the response, the thermospheric response, we remove the quiet time response, and we keep the, oh, sorry, here are the thermospheric wind, the whole components of the wind, I'm sorry. And we compared with the model. And of course, the results are not very satisfactory, because the model does not, it is not a dynamic model, so it won't give a realistic prediction. And it happens that we have a GPS, and we compared the result of the GPS. So, am I taking too much time? It's okay?
Yeah, you're good.
Okay.
Just 10
So
more
we
minutes.
have,
yeah.
okay, thank you. So we have the tech measurement for a very quiet time during this specific month where the geomagnetic storm occur, and the 27, 28, the night where the storm occur, and we witness a traveling ionospheric disturbance in this. We witness, first of all, a positive storm with traveling ionospheric disturbances. And when we superpose these two figures with the meridional winds, we made very interesting results. Meaning that the ionosphere was charged with positive, but even though it was positive, in the vicinity of the traveling atmospheric disturbance and the traveling ionospheric disturbances, we remarked that there was an anti-correlation between HMF2 and MF2. Meaning that inside of a traveling ionospheric disturbances, the thermospheric ratio have an opposite trend of its normal trend. Okay. This is called the traveling atmospheric effect. And we have confirmed this result in this specific night. And for the same night, we were lucky that there was some equatorial plasma bubbles, and we witnessed them, and the study of these bubbles give us the electrodynamic response of the ionosphere during that time, and we observe a reversal of a background electric field, and we return. This is the drift, the drift of the equatorial plasma bubbles that tend to match exactly the zonal wind during the storm. All right. This is what is green here is it's quiet time, and this is disturbed time, and this is the plasma bubbles, which give us an idea about that the dynamo was fully activated in the area where we have achieved this measurement over OK Meeting Observatory. And in another paper, in another paper, we studied all the storm that happened in about 3 years measurement, and we give just a statistical tendency. We remarked that about 60% of the cases are characterized by traveling-induced circulation, meaning traveling atmospheric disturbances and traveling ionospheric disturbances. Here we have in blue just the storm effect, meaning in the atmospheric wind, we subtracted the quiet time in the meridional wind and the quiet time in the zonal wind. So this disturbed zonal wind are completely east-westward, and the disturbed meridional winds are wavy. There is some traveling atmospheric disturbances, sometimes two, and the second one is trans-equatorial, and sometimes three traveling atmospheric disturbances. In 33%, there is very slight difference between quiet time and disturbed times. And in 8% of the case, we have trans-equatorial winds during the whole night. This it's very interesting, this statistical result. It gives us an idea about what happened in the globe in general. Some regions are going to feel are going to be hit directly by the atmospheric winds coming, and for some reason they are not going to be hit that much, and will for the same KP, same DST will experience just slight difference between in 30% of the case, they will almost see a very low difference between quiet time. Maybe because the Hadley cell of the storm does not fully develop to the area of the air globe. I don't know. It's very interesting to comprehend what's happened over the globe in general.
We have 2 minutes more.
Oh, sorry. Oh la la. 2 minutes is very low. So we made also another study when we studied a superposed epoch analysis to have an idea about what happened of course, by using the whole storm, what happens in every phase of the storm. And so I cannot go through the details. I will just give slides and go here in the slide. We compare with the models, and it's very interesting. This one is very interesting because it is a longitudinal study. We have two sets, Marrakesh and Pa, and they are in the same longitude, in the same geographic longitude, and how they respond together in quiet time and in their climatology and during geomagnetic storms. Is very interesting because the fact that OK Meeting is closer to the magnetic equator, it will witness the wind very differently. And in the area of the air globe, let's say, for example, the zonal winds align completely with the magnetic equator. The neutral zonal winds align with they turn westward in aligning with geomagnetic equator, but not with the geographic equator. And this gives the general trend of the differences between what happened here and here. And of course, OK Meeting will feel the storms much harder than PAR, because of the fact that it is closer to the geomagnetic equator. So there's too much to go through details. This is what explains what happens. You see, this is the zonal winds, the thermospheric zonal winds that tend to align and explain the trend, the general trend. Okay, and this is the response. This is the comparison of the response of what happened in Oakhamden and what happened in Par. Two storms. Okay, and yes, we tried to analyze also the effect of the study, the asymmetry, the equatorial ionization anomaly over Oakhamden Observatory, and try to find some correlation with the thermospheric winds. We averaged it over 3 years, but the rule never coincide with the zero. Maybe I don't know. Maybe people that work on that can give me explanation why. Maybe the equator has shifted somewhere. I don't know. It is always in -3 degree, and so there is a lot of and we try to, which is important regarding the thermospheric wind, that we observe symmetrical equatorial ionization crest generated by, and statistically, by weak conversion of divergent meridional winds in both hemispheres. And we observe statistically the asymmetry with trans-equatorial winds. And the southward meridional winds have a tendency to enhance the northern crest equatorial ionization anomaly during quiet time and in a more pronounced way during geomagnetically disturbed conditions. And this is my last slide. That we have in Africa now 5 GPS, and hopefully we'll have even more. The fact that, sorry, not 5 GPS, 5 FPI. And the fact that the FPI measures in 500 kilometers, we can, yes, 500 kilometers apart. We can, like, say, for 1,000 kilometers square, we can put just 2 FPIs and have a good proxy about the thermospheric, the primary source driving the thermospheric dynamics. So we don't need that much in order to map an area and to study it. This is my last slide.
Wow. Thank you, Dr. Aziza. That was fantastic. Thank you. It's very interesting to see how powerful the FPI is, where you can actually use few of them to study spatial and temporal variability.
Yes, because as I said, it measures here and here and here and here. It gives us in a sequence five times the in different. So we can put another circle here, another circle here, and you have all the area of Morocco and some of Algeria.
Exactly. Interesting. Yeah. Do we have questions? Yeah, we have like 5 minutes more. We don't usually want to go over 1 hour because we know people are busy and we don't want to step into more than 1 hour. So sorry about that. I tried to rush you at some point, so I'm so sorry.
Yes, you're right, because I have too many slides and I did not put a summary. I could, but I say, well, maybe we can go far in the details, and I don't know. So I kept so many slides.
Yeah, if somebody wants to have some detail, you can ask some questions. Dr. Aziza will be happy to answer your question. Yeah, please go ahead, Yinka.
Thank you, Olu. Thank you, Aziza, for your talk. Very interesting, very interesting studies. I will definitely take a look to the last study you showed about the asymmetry. I think it's very interesting. I'm curious about one thing that you presented at the beginning. I think it was in slide 3, regarding the current situation of the GNSS stations that you have in Morocco. I don't know if in slide 3 are showing all the available GNSS stations, or this is a selection of stations.
No, there are others GPS station. There are many GPS stations, but to access to the data, they belong to private societies.
Ah, okay. Yeah.
You know?
Yeah, that's
And
what I imagined. Yeah.
We have to apply for the data. We have to look to have somebody to give us the tech. They just map cartography. They don't go back to the tech, and they keep the results from themselves. And it's very hard to. It is feasible, but we did not look.
So it's
So those
private.
the results are in the IGS database. And
okay. Thank you very much.
I think CONGA will cover part of Morocco, right? I'm not sure, but we'll be happy to release our data.
Or maybe we can expand a little bit.
Very soon we're going to expand to Morocco.
We wanted, yeah, because we do not have funds to give them money. So when they find a job, they just leave and they go. And so they have reached a certain age. They want to be independent from their parent, and so they just. Yeah. And we did not get lucky with the GPS data. We wanted to have more and to study it thoroughly and have the results. Hopefully, maybe in the future we can.
Something
so
interesting. Okay, go ahead.
This GNSS station that we are seeing in the map belong to the IGS network?
Yes.
All of them?
I think so. Arabat, yes, Tétouan. Maybe Oukaïmeden, we can have the data of Oukaïmeden and the Rabat. Yes, I think so. Yes, Rabat, surely.
Okay, thank you.
Yeah, a lot of science discussion, Aziza. Thank you so much. I was like, there is one figure that you showed that actually show large differences between the zonal components compared to the other components. Do you know what is responsible for that?
Which one? This one or this one?
There is one of the first one that you actually mentioned that in the discussion.
This is quite time response.
Okay.
This is quite time and the 5 components.
That showed the closeness between the poleward and the equatorward, and then you show the large difference between the zonal, the westward and the eastward. I was like, oh, I think it's this one. Yeah, that one there. The down
this one in the left here?
No, on the left, bottom left.
Bottom here?
Yes, I think.
Yes.
Yes.
This is very quite nice. There is some dynamic of some waves coming, and it will be very interesting to to study thoroughly the very quiet time. The zonal components, they stay close to one another. They stay close to one another only when there is a gravity wave that breaks down and they deposit the energy, like here. We have a signature of gravity waves breaking down and giving this wavy pattern on the vertical winds and the abatement of the other components. Here, for example, we have the 2 components, the meridional wind, they stick to one another, meaning that something came to the area, something, it is not within the vicinity of the area, it's coming, it's, if we develop some procedure, I want to say if we are intelligent enough to develop some procedure to extract the external component and which wave it is, which type, with DE3, I don't know, SE2, or to see what it's about.
Yeah, excellent. Thank you, Dr. Aziza. Thank you so much. Any other questions for her? You may stop sharing your screen. Let me see if I can help you with that. Can you stop sharing your screen, Dr. Aziza?
Okay.
Let me see. Close.
Uh-oh.
It disappeared. Okay, good. Thank you.
Hmm.
Yeah, so let me see. If there is no question, I think we are at the top of the hour. Let me just see if we have anything we want to talk about here. Final one. Yeah, I think that is our presentation today. We usually open the floor for discussion, and we won't be able to do that today because we run out of time. In the next meeting, we hope to be able to open the floor for discussion. Yeah, Solomon, you are saying something? Hello?
Yeah, service has gone back now.
Okay. You may type your question. You may type your question if you have a question. Yeah, that would be helpful.
Wait. They brought somebody from India to maintain.
I think I need to mute some people. So yeah, so that is part of the right. And we still encourage you to present your work if you feel like that, particularly when it has to do with instrumentation over Africa. And we also welcome science talks. It helps us to discuss more of what the instrument can do, like Dr. Aziza show what the FPI can do. Oh. Dr. Shigo, can you help me mute some people if they keep disturbing the flow here? So that would be very good to have different type of people, different type of discussions with from different people who are interested in this instrument, and this will also help us to put the instrument into perspective, science perspective, so that we know the capability that that the instruments can be useful for. And knowing it is one thing and seeing it is another thing. So it's make it interesting when you show the results, like Dr. Aziza just did. It's very, very interesting. It's intriguing to see those results. So thank you so much, Dr. Aziza, again. And I think that will, if we don't have any other question, let me see here. If we don't have any other question, hands raised here. All right. Can easily mute people. So yeah, thank you all for coming. I think that will make it the end of the today program. Thank you so much. We'll see you next month.
Okay, you're welcome.
Thank you. Thank you, Patrick. Thank you. It's good to see you.
Thank you.
Yeah.
Thank you. Bye-bye. Thank you.
Thank you. Thank you. Bye. Yeah.
Well done. Bye.
Bye. Oh,
thank you, Dr. Olu.
Thank you.
Thank you, sir. Professor Radio.
Sorry?
Yeah. How are you? Professor David, God bless you.
Prof, sir.
All right. Well done.
Prof, sir, good evening, sir.
Yeah, good evening. Thank you. Hey, nice Bolaniwa, you said you will install the GNSS. I've not heard from you.
Yes, sir. We are on it. We have installed the antenna. We have installed the antenna. We have done everything, but we need approval from the DC. The location that we place the antenna, we need approval so that we can install we can complete the installation, sir.
When you install this, you come and give a talk on your experience at this CONGA meeting. After you must have done the installation and take measurement for 1 or 2 days and share with Professor Adebesi. Then you give a presentation on this CONGA meeting.
All right, sir, no problem.
That is interesting, Prof. That is so
No problem, sir.
interesting.
Is to install a low-cost GNSS receiver that we got here. The low-cost GNSS is the one is to install in their location. They have it already with them.
Oh.
All right.
So we'll be looking
All right.
forward to that. Maybe next year we have a lot of MTL, I mean spatial
Slot. Okay.
slots. Yeah.
Okay.
Yeah. So let us know.
All right.
no
Okay.
problem,
Thank
sir.
you.
All right,
Thank you,
sir.
Prof. Thank you so much.
All right. Bye. I will
Yes,
send you. I will send you chat
Prof,
and message. All right. Bye. Yeah.
Yes, sir. Thank you, sir.
Yes, sir.
Mr. David,
Thank
bye,
you.
sir.
Bye.
Yes, sir. Yes, sir.
Bye.
All right. Thank you.
All right. Bye, sir.
Bye-bye.
Bye.
Yeah. Bye.
Bye, sir.
Thank you.
Okay, bye-bye.
Thank you.